now going to discuss certain proofs of certain results that we have mentioned in the earlier lecture. First one is division algorithm. So division algorithm, this result already you know that if you have some integer b greater or equal to 1 and you divide another integer a by b, then there exists unique quotient q and remainder r, where this r may be 0 or it may be less than b. So using the well ordering principle of positive set of positive integers, we can prove this. Okay, so essentially division algorithm, here we have mentioned b greater or equal to 1. It can be proved for any b not equal to 0. When a is divided by b, there exists unique quotient q and unique remainder r such that a equal to bq plus r. Let us now go through the proof. So we considered this subset of integers a minus bx. The collection of all integers, of this form a minus bx, where x is some integer. X may be positive, may be negative, and a minus bx, this is positive, greater or equal to 0. Okay, so this is a subset of natural numbers. Now, first claim is S is non-empty. You can see that this b, in this condition b is greater or equal to 1. And we know that mod b is always greater than 0. So both sides you multiply by mod b, mod a, multiply by mod a. So b greater or equal to a implies mod a b greater or equal to mod a. Okay. Now what is the value of a plus mod a b? This is greater or equal to a plus mod a b is greater or equal to mod a. So this value is always greater or equal to 0. So we can see that this is a number, this is an integer a plus mod a b greater or equal to 0. This is an integer greater or equal to 0, and you can treat it as an element of a minus bx, where x is minus of mod a. X is minus of mod a. So this integer is of this form. So it belongs to S. So S is non-empty. Now, well ordering principle says that if you have a non-empty subset of positive integers, then A must have a least element. Okay, so here we have a set S, subset of integers, positive integers, and it is non-empty. So it must have a least element. So non-empty set of non-negative integers. So its smallest element is either 0 or any other positive integer. Okay, so smallest element exists. So suppose R is the smallest element of the set S. So R is the smallest element of this set, means R is of the form A minus b. Suppose I take this to be q. Q is some integer a minus bq. So R equal to R is the smallest element of this set, so it will be of the form a minus bq. And this R is either 0, it can be 0, or it can be some positive integer greater or equal to 0. Okay. Now we have to show that this R not only greater or equal to 0, it must be strictly less than b. Okay, this is my next claim. R is less than b. Okay, so what we have to show that A can be written as bq plus R. I have written R to be this one, so A equal to bq plus R. R greater or equal to 0. I have to show this R must be less than b as well. Okay, so you can prove it very easily. R less than b, you have to show that. So suppose R is not less than b, so it is greater or equal to b. So if you consider a minus b times q plus 1, a minus b times q plus 1, this integer can be written as this is a minus qb minus b, r minus b greater or equal to 0. So we are able to construct an integer, find an integer a minus q plus 1 b. So this is also a minus b x b type, and it is greater or equal to 0. So a minus x b type greater or equal to 0. This means it must be an element of S. So here we can find an element which is in S. Now this element is smaller than the element a minus bq. A minus bq plus 1 is smaller than a minus bq. So if we assume r greater or equal to b, then we can see that this integer a minus q plus 1 b, this is an element of S, and which is smaller than the element a minus bq. This actually contradicts the fact that r is the smallest element. R was the least element. By choice, R was the least element of the set S. But if R greater or equal to B, then we can get this integer smaller than the smallest element R of the set. So this is essentially a contradiction, as R is the least element. So this R greater or equal to B, this is wrong. This is wrong. So R must be less than. Okay, so we have proved that A can be written as BQ plus R, 0 less or equal to R less than B. So only thing we have to show uniqueness. It is unique. This B and Q, this Q and R are unique. So if they are not unique, suppose they are not unique. So the third claim is they are unique. If they are not unique, suppose there exists Q prime R prime. So that A can be written as BQ plus R, as well as A can be written as BQ prime plus R prime. This R lies between 0 to B, including 0. This R prime also lies between 0 to B. 0 to B. So if you take R prime minus R, this will be equal to B Q minus Q prime, or B Q minus Q prime absolute value equal to R prime minus R. We have taken B to be greater or equal to 1. Okay, so so from here I can argue that since R prime is within this range, and R within this range means minus R lies between minus B to 0, less or equal to 0, then R prime minus R lies between minus B to plus B. That means this value, this is less than B. R prime minus R less than B. So Q minus Q prime absolute value is less than 1. So B absolute value Q minus Q prime equal to this is less than B. Okay, so Q minus Q prime is less than 1. Q minus Q prime less than 1. Now Q and Q prime are integers, and it is only possible Q minus Q prime less than 1, difference between two integers less than 1. It is possible, only possibility is Q equal to Q prime. So we have established Q equal to Q prime, and Q equal to Q prime essentially means R equal to R prime. Okay, so this Q and R are unique. Okay, so the restriction on B was B greater or equal to 1. You can extend this proof for B not equal to 0. Okay, so you can just go through this. Now this theorem, it is also called Béjou's identity. It says that if two integers a, b not both equal to 0, and suppose d be the GCD of a, b, then there exist integers x and y such that this GCD, it says that this GCD can be written as a linear combination of a and b. integer linear combination. So these integers x and y you can always identify such that they can be written as ax plus by. This is called Bezoar's identity. And mind that this x and y not necessarily unique. There may exist different pairs of x, y, so that this condition is satisfied. And a special case when a and b are co-prime, in that case d is 1, and in that case 1 equal to x plus by. So this result, the proof that we are going to discuss. This is existential proof. This is not constructive proof. This essentially gives a way to just existence proof. It does not give a way to calculate d or x or y. Given a and b, how to find d or how to find x and y, this proof will not give that information. Okay, so we will discuss Euclidean algorithm and also extended Euclidean algorithm to find DCD as well as x and y. We'll discuss those algorithms. Okay. Now here also this proof is also uses the well ordering principle of set of positive integers. So you can consider the collection of all integers of the form x plus by. Given a and b, consider the set of all points x plus by, all integers x plus by. X and y are integers. Means they can be negative integers also. Okay, and this ax plus by must be greater than 0. Must be greater. This is the collection of all such integers ax plus by, xy integers, and ax plus by. This is greater than 0. So this is a subset of non-negative integers, and you can prove that this is non-empty. This is non-empty. Means if you consider simply mod A, so mod A can be written as A into x plus b into 0. Okay, mod A can be written as A into x plus b into 0. A is means at least one of A and B is non-zero. Suppose A is non-zero. Okay, mod A, so A non-zero means mod A is always greater than 0. So if you consider this integer mod A equal to, you can write it as ax plus b0, where x is 1 if A is greater than 0, x is minus 1 if A is less than 0. Okay, so mod A is always greater than 0. That means ax plus b0, this is an element of this set, x and 0 integers, and ax plus b, this is positive integers. So mod A is an element of this. So this is non-empty subset of positive integers, non-negative integers. Non-empty subset of positive integers. So by well ordering principle, it must have a least element. This set must contain a least element. Suppose the least element be D. We denote it by D. D is the least element. Okay, and suppose D equal to AU plus BV. For UV belongs to two integers UV, I can identify such that the least element of this set D can be written as AU plus BV. For sub integers UV. Okay, so we have to show that this least element of this set, this least element is essentially the GCD, means greatest common divisor of A and B. So our first claim is to prove D is a common divisor of A and B, and second claim to prove it is the greatest common divisor. Okay, so essentially you can define the GCD of AB in this way also. Okay, so GCD of AB to be the least element of this set. Least element of this set. This is an alternative definition. You can take this also an alternative definition. However, we will complete this proof this way. So D is a common divisor of A and B. So common divisor of A and B. So if if you apply the division algorithm on A and D, then A is dq plus r. So applying division algorithm, you divide A by D, then you get suppose it is not a divisor of A, or it is not a divisor of B. So in that case, division algorithm, you can get A equal to dq plus r. Q and R are integers, and this R, it can be 0 or it is less than D. You are dividing A by D. So by division algorithm, this will get. Now this R is A minus DQ. A minus D is essentially AU plus BV. AU plus BV Q. So we can write it as A linear combination of A and B with A is multiplied with the integer 1 minus UQ and B with minus VQ. Okay, so we have to prove that D divides A. That means this R is essentially 0. If R not equal to 0, then what happens? If R is not equal to 0, then you can say that R is of the form AX plus BY type. R is of the form AX plus BY type, which is positive integer. If it is not 0, it is greater than 0. It is greater than 0, then R is an element of S. But this R is less than D. D was R is less than D. By division algorithm, R is less than D. So it actually gives us a contradiction. If R belongs to S, from here I can write R in this way. It implies R belongs to S. But D was the smallest element of the set S. But here I can get another element R, which is smaller than D, the smallest element of S. This is a contradiction. So R cannot be equal to 0. R must be 0. So when you divide A by D, there will be no remainder. Same way you can prove that B also has D as its divisor. Okay, so so A equal to DQ, also similar way you can prove that D equal to some DQ prime. Okay, so D is a common divisor of A and B. Now we have to show it is the greatest common divisor. Okay, this is the greatest common divisor. To prove this, you take another common divisor of A and B. C is another common divisor. So C is a divisor of A as well as B. C divides A, C divides B. So by linearity property of divisibility, C divides A U plus BV. That means C divides D. Okay, so this proves that D is the largest divisor of A, common divisor of A and B. Okay, so if you take another common divisor of A and B, then this common divisor essentially divides D. So D is largest. Any common divisor you take, C, the common divisor of A and B, that always divides D. That always divides D. This proves that D is the greatest common divisor of A and B. So essentially, so this GCD, how we obtain this GCD? This is if you consider this set, then this divisor, this GCD of A and B is the least element of this set S. Okay, least element of this set S. Now we are interested in how to find this X and Y as well as D. We will discuss those things. So this proof using well-ordered principle, you can prove this. And given to positive integers, given to integers A, B, where both not 0, if A and B are co-prime, means A and B are co-prime, if and only if there exist integers UV such that 1 equal to AU plus BV. Two integers are co-prime if and only if there exist integers UV such that 1 equal to AU plus BV. Thus this proof is very straightforward. Means if and only if you have to prove both ways. If A and B are co-prime, that means GCD is 1, GCD of AB is 1, then by the previous result, Bezout's identity, GCD can be written as linear combination of A and B, integer linear combination. So AU plus BB. This part, if part is okay, only if part. That means if GCD, if there exist integers u and v such that 1 equal to u plus bv, then you have to argue that GCD of AB is 1. GCD of AB is 1. This is also straightforward. Suppose this relation holds and GCD of AB is not 1. GCD of AB is D. Then what you get, D is GCD of AB. This means D is a common divisor of AB. D divides A, D divides B. So D divides AU plus BV. That means by the linearity property of divisibility, D divides A, D divides B means D divides AU plus BV. That means D divides 1. So this holds only when D equal to 1. That means GCD should be 1. So very simple proofs. Maybe you are already familiar with this. This is another important result we are going to use. While discussing. Already we have used these things. And if D is GCD of AB, then A by D, B by D, they are relatively co-prime. Okay, while discussing the solving how to solve linear congruence, there we used this, that if D is GCD of A and B, then GCD of A by D, B by D is 1. Okay, means A by D, B by D are relatively co-prime essentially. Okay, this is relatively prime, or they are co-prime. A by D, B by D is relatively prime. Proof is very easy. D is a divisor of AB. So D divides A, D divides B. So there exists some integer m such that A equal to dm, and there exists some integer n such that B equal to dn. D is a factor, right? D is a factor of B. So there exists n such that B equal to dn, and there exists m such that A equal to dm. So A by D is integer, B by D is also integer. These are integers. Okay, these are integers. Now, since GCD of AB is D, by Béjau's identity, you can find integers UV such that D equal to AU plus BV. Or you can rewrite it as 1 equal to A by D U plus B by D V. Now, A by D is integer, B by D is also integer. So, you are getting 1 equal to MU plus NV. This is M, this is M. Okay, so what does this mean? M and N are relatively prime. M and N are co-prime. So this MU plus NV equal to 1 means GCD of Mn equal to 1. GCD of Mn equal to 1 means A by D, B by D, they are co-prime. So you have to prove this. Using Béjau's identity, you can easily prove this. Next one is, this is also simple. If A divides BC and A and B are co-prime, then A must divide C. This is also, means if A is a divisor of BC and A does not divide B, then A must divide C. That we already know. But how to prove that thing? Okay? So using Béjau's identity, you can prove this. GCD1 means there exists integers UV such that 1 equal to AU plus BV. AU plus BV. Now, you multiply both sides by C. So, C equal to ACU plus BCV. Now, A divides this part. A divides BC also. It is given. A divides BC, A divides AC always. A always divides AC. So A divides C. A divides C. Okay, this way you can prove. Just one line, one or two line proof. A divides C. Okay. This way you can simply using Vedor's identity, you can prove this thing. Okay. This one also using Vedor's identity, you can prove this. This says that if A divides C, B divides C, and A and B GCD is 1, then AB divides C. Okay, A divides C, B divides C, A and B are co-prime, then AB must divide C. Okay, so A divides C, B divides C. This means A is means A divides C, B divides C. So C equal to some AM, C equal to some BN. Okay, C equal to AM, from this C equal to AM and C equal to BN for some integers M and N. Now GCD of AB is 1, means 1 equal to AU plus BV, where UV, you can always find this UV. How to find? We haven't discussed yet. But by existence theorem, you can find this UV such that 1 equal to AU plus BV. Now, if you multiply this equation both sides by C, then C equal to AUC plus BVC. Now C value, this is AM and BN both, so you can utilize this. AU, BN, BV, AM. So AB times UN plus BN. So C can be written as this. So this implies that AB is a factor of C. AB is a factor of C. Okay. So if A divides C, B divides C, and AB are co-prime, then AB must divide C. This way you can establish this fact. Now Euclidean algorithm. Euclidean algorithm, it finds the GCD. And it actually uses this fact. It actually repeatedly applies the division algorithm. Euclidean algorithm consists of repeatedly applying the division algorithm. Okay, it is based on the following simple property: A, B, Q, R are as in the division algorithm. That means when you divide A by B, you get integers. So this relation holds. You get unique integers Q and R such that A equal to BQ plus R, where R is lies between 0 to B, including 0. This is the division algorithm when you divide A by B. Q and R unique integers. Now, so it holds that GCD of AB is same as GCD of BR. Means you already know how to find GCD. It means generally we use generally in elementary maths we find the GCD like this. Keep on dividing. Means divide A by B. Whatever remainder, remainder and whatever remainder you get, then that remainder becomes the divisor. And you divide B by that R. That way, ultimately, you get 0. When you get 0, then the previous before that step divisor is your answer, the GCD. Okay, so same concept. This is essentially uses this concept. So you know how to do that. Working procedure you know, but why it works? This actually comes from this fact. The GCD of AB is same as GCD of BR. This is your division algorithm. GCD of AB is same as GCD of BR. Okay, proof is very simple. So A equal to BQ plus R. Now, what does this mean? That means we have to establish so if you consider collection of all common divisors of AB, we consider collection of all common divisors of AB and collection of all common divisors of BR. So we construct two sets: set of all common divisors of AB and set of all common divisors of BR. And we are going to show these two sets are essentially same. Therefore, greatest element of this set and greatest element of that set are also same. That means GCDs are same. Okay, this is the idea. So we consider the common divisors of B and R. So if E is a common divisor of B and R, E divides R, E divides B. Then from this relation, we can say E divides R, E divides B means E must divide A. Okay, so E is sitting inside B. E is also sitting inside R as a factor. That means E is sitting inside A. So E divides R, E divides B implies E divides A. So all the common divisors of B and R, it is also a divisor of A. Again, you consider if you rewrite this equation in this way, R equal to A minus BQ. Then you can say that if you take the common divisor of A and B, so this equation and this equation are same. We are just rewriting it. Now you consider the common divisors of A and B. Here we have considered common divisors of B and R. Here we consider common divisor of A and B. So if A is a common divisor, E is a common divisor of A and B, E divides A, E divides B, then you can say E divides A, the E divides B implies E divides R. So this essentially proves that common divisor of R and B proves that the set of all common divisors of R and B also equals the set of all common divisors of A and B. Okay, the collection of common divisors of R and B, their collection of is same as this. That set is same as the collection of all common divisors of A and B. This implies E common divisor of R and B means it is also divisor of A. So it is a common divisor of both R, B and A, all three. Similarly, here also E common divisor of AB means it also divides R. So it is a common divisor of A, B, R. So it implies the collection of all common divisors of R and B, that set, and the set of all common divisors of A and B, these two sets are essentially same. Okay, so greatest element here is essentially the greatest common divisor of B and R, and greatest element here, greatest common divisor of A and B, they are essentially same because both the sets are essentially same. So directly follows from this argument. Okay. Now Euclidean algorithm. Euclidean algorithm already you know. So a pair of integers AB is your input, not both 0. You have to find the greatest common divisor. This is the working procedure. Apply the division algorithm repeatedly. So first you write, suppose A is greater or equal to B. Okay, so if it is not the case, then you switch the roles of A and B. Okay, switch the roles of A and B. So apply the division algorithm to write A equal to B, Q0B plus R1. Okay, when you divide A by B, quotient, you say this quotient is Q0 and remainder is R1. If remainder, this R1 is 0, then we say the GCD of AB equal to B. Otherwise, continue dividing the successive divisors by successive remainders until a 0 remainder is reached. So, if R1 not 0, then you divide B by R1. So, by division algorithm, you can write B equal to sum Q1 R1 plus R2. 0 less or equal to R2 less than R1. So, this R2, now we are dividing B by R1. So, this R2 must be less than R1 or it can be greater or equal to 0. Okay. So here when I write first time A equal to Q0 plus B plus R1, this R1 is less than B. R1 greater or equal to 0 and less than B. R1 lies between 0 less or equal to R1 less than B. Similarly, when you divide, the next step, if R1 is not 0, then you divide B by R1. So this remainder lies between this range. Then if it is not 0, then R2 becomes your divisor. And divide R1 by R2. Remainder R3. That way, keep on doing this until you get this remainder 0. So after certain steps, it will always be 0, because each time your remainder is decreasing. So initially it was R1 0 less or equal to R1 less or equal to B. So so you in the last step you are getting 0 less or equal to Rn less than Rn minus 1. Less than R2, R2 less than R1, R1 less than B. So when you keep on doing this, your remainders become smaller integers. And after finite number of steps, you are getting essentially this Ri, this sequence, this is a sequence of integers, decreasing sequence of integers. So it is the sequence must converge. It is a decreasing sequence, positive integers, it must converge. So essentially, you are getting a sequence of remainders strictly decreasing in order. B greater or equal to R1, greater than R2, greater than Rn. These are greater than 0. Okay, so the algorithm must eventually terminate this sequence. This Ri must converge. Okay, it will eventually terminate. At most B, after at most B steps, it will terminate. Okay, so from here I can say if you apply the previous result, GCD of A Q0 equal to GCD of B R1 equal to GCD of R1 R2 equal to GCD of R2 R3 equal to GCD of like that. GCD of R2 R3, GCD of Rn minus 1 Rn minus 1 Rn equal to GCD of Rn 0. Now GCD of Rn 0 is 0. If one element is 0, this GCD of Rn 0 is Rn. If both are 0, we take GCD to be 0. If one is 0, then means in this case it is Rn. Okay? So GCD of AB is Rn. Means when you get remainder, ultimately last remainder is 0, then this Rn, this divisor is the. Okay, so you can write the program. This is your recursive call. A mod B is essentially your R. Then you replace A by B and B by R. Okay, until you get your B is 0. While B is 0, you come out from the loop. And the value of A, the return A, ultimate A will give you the result. Okay, so time complexity means how many times it will repeat. This is essentially log n square bit operations. Okay, so if you have any integers, any two natural numbers, A, B, suppose less or equal to n, then n is the size of n is log n plus 1. Okay, then addition requires log n bit operations, subtraction also log n, multiplication is log n square, division is log n square. Modular, actually we are doing modular operations, modular division. Okay. Now this one, these are very easy things, you just go through these things. Okay, so very trivial things. If P is prime and you take any integer less than P, positive integers less than P, then A must be co-prime to P. Using Bejour's identity, you can, it's not Bejour's identity, you can prove it by yourselves. Okay, so if P is any integer, if you take any integer, P is any prime, and you take any integer less than P, positive integer, then it must be co-prime to P. The GCD of AP must be 1. If it is not 1, suppose D, then D divides A, D divides P. Now D is a prime, D divides P implies either D is P or D is 1. Okay, so from this fact you can argue that since P is a prime, if D is GCD of AB, we have to show GCD of A and P is 1. So the A and P are co-prime, that means GCD of AP 1. If it is not 1, suppose D. So this is GCD means D divides A, D divides P. D divides P implies P is prime, so D must be either P or 1. Also A less than P and D divides A. D divides A is less than P and D divides A. D divides A. A less than P and D divides A, so D cannot divide P. D divides A, D cannot divide P. D cannot divide. So D equal to GCD of AP. That means D divides A, D divides P. P is prime. D divides P implies either D equal to P or D equal to 1. But here from given condition, A is less than P, A is less than P and D divides A. This implies D cannot be P. D divides A means D cannot be P because P is greater than A. P cannot divide A, okay? So D cannot be P. So D must be 1. So A and P, they must be co-prime. If you choose A to be a positive integer less than P. If P is prime, A is an integer greater than P, such that P is not a divisor of A, then P is co-prime to A. Okay, so it says that now suppose P is prime and you take an integer greater than P. In this theorem, we have chosen A to be less than P. Positive integer less than P. Now you choose an integer A to be greater than P. P is prime, such that P is not a factor of A. Not a factor of A. Then P must be co-prime to A. So this also you can prove very easily. Suppose the GCD of P and A is D. So D divides A, D divides P. Now P is a prime, D divides P. This implies D is either P or 1. D is either P or 1. But D cannot be P, because if D is P, then since D divides A, so D equal to P means P divides A. So P is not a divisor of A. So D cannot be equal to P. D must be 1. So in this case, it is prime. So given a positive integer, if you pick an integer to be less than P, positive integer less than P, it is co-prime to P. If you take a positive integer greater than P, which such that A does not have P as a factor, then also AP are co-prime. Okay, so here p is a prime. If p is a prime, a is an integer greater than p, such that p divides a. Okay, so you take an integer greater than p and p divides a. Then GCD of AP is b. Take this as exercise. Okay, very simple. Now this lemma also we have mentioned in the earlier lecture that if p is, suppose p is a prime and a b two integers, if p divides a b, then either p divides a or p divides b or p divides both. And you can generalize this that if p is a prime and a1 a2 an are integers, suppose p divides this product a1 a2 an, then p must divide at least one of a1 a2 an. Okay, so p is prime and a1 a2 are integers. P divides a1 a2 an means p must divide one of them. So first one we have to show that if p divides AB, then either p divides A or p divides B. So p divides AB, and suppose p divides A, then we are done. If p does not divide A, suppose p does not divide A, we need to show p must divide B. Now p is prime, and if p does not divide A, then by the earlier theorem we know that p and A must be co-prime. We have shown that if you take an integer A to be a positive integer less than p, then GCD of AP is 1. If you take A to be a positive integer greater than p, which has p, which does not have p as a factor, A does not have p as a factor, then also GCD of AP is 1. Okay, so if p does not divide A, since p is prime, we must have this thing, GCD of AP equal to 1. P does not divide A. So if A is less than p, it is GCD is 1. If A is greater than p, then since p does not divide A, GCD of AP is also 1. So by Bejour's identity, we can write this as 1 equal to AU plus or AX plus PY. 1 equal to AX plus PY for some integers XY. So if you multiply both sides by b, b equal to abx plus pby. Now you can see that in this equation, on the right hand side, it is given p divides ab, right? The p divides ab, and this one already contains p. So p divides this part also. So p divides this whole thing. P divides b. Okay. So in this case, we have shown if in case p does not divide a, then we have shown p divides b using this Bejour's identity and the previous two theorems. Okay. So p divides this right hand side means p divides b as desired. Okay, so the next result also you can achieve. Just go through it. This is the first one was the special case. Okay, you can go through this. Same way you can prove. I will not discuss this. This also fundamental property of composite numbers. A composite number has at least one prime divisor. A composite number has at least one prime divisor. I think I have used well ordering principle. Okay, well ordering principle. Using well ordering principle, there are several ways you can prove this part. This result, composite number has at least one prime divisor. So n is composite. So composite means it is not prime. That means it must have a positive divisor other than 1 and n. We have to to establish that it has at least one prime divisor. One prime divisor. How to prove that? So if it is a composite number, it must have one divisor other than 1 and n. So you consider S to be the set of all positive divisors of n, this composite number, which are different from 1 and n. Which is different from 1 and n. So the S is non-empty because since it is not prime, it must have one positive divisor other than 1 and n. So if you consider this set of all positive divisors of n other than 1 and n, then it must have one element. It is non-empty. So we are getting, we can apply the well ordering principle because S is a non-empty subset of the set of positive integers. So it must have a least element. We call the least element to be D. So least element means this set S is the collection of all positive divisors of n different from 1 and n, and D is the least element of that. So D is a positive divisor of n, least positive divisor of n, and it is different from 1 and n. So D lies between 1 and n. So we have to show that this D is essentially a prime number. So D is the least positive, least element of S. Okay, so we have to show D is prime. If it is not prime, what happens? If it is not prime, then it must have a divisor D prime other than D and 1. Okay, so this is the property of composite number. If D is not a prime, then it must have a divisor D prime lying between 1 and n. And D prime must be less than D. Because D prime, I am assuming D prime is a divisor of D. D prime must be less than D. So we'll get this. Now D prime is a divisor of D. That means D prime divides D. And D divides n. D is a divisor of n. Okay, D was the least element of this set, consisting of set of all positive divisors of n different from 1 and n. So D divides n. D divides n, and D prime by assumption D prime divides D. So this implies D prime divides D. D divides n. The transitivity property of divisibility. It says D prime divides n. So I can get, if I assume D is not prime, it is composite, then we can get another divisor of n which is smaller than D. But D was assumed to be the least element of S. But we are getting even smaller element than D, which is in S. It is giving a contradiction because of the nature of the contradiction of D's behavior. D was assumed to be the least element of S, but if we assume D is not prime, then it is not prime, then in that case we get a contradiction. We get another positive integer D prime in the set S, which is smaller than D, smaller than the smallest element of D. So we are getting the smallest element of S. We are getting a contradiction. So this way, so our assumption that D is not prime, it must be false. So D must be prime. Okay, so every composite number has at least one prime divisor. Okay. Okay, this is the fundamental theorem of arithmetic, also called unique factorization theorem. It's also mentioned. Okay, so every positive integer can be uniquely expressed as the product of primes. Every positive integer can be a greater than 1 can be represented as uniquely expressed as a product of primes. So a can be written as p1 to the power alpha 1, p2 to the power alpha 2, pn to the power alpha n, where alpha 1, alpha 2, alpha n, these are positive integers. And unique, this is unique, this representation is unique, up to the given ordering. So if you say given ordering in the prime, this p1, p2, pn are prime numbers, p1 less than p2 less than pn, then this representation is unique. And so there is some note. 1 is not a prime number. 1 is never considered as a prime number. Why? Because you will not get unique factorization in that sense. If any one is not considered as a prime number. Because if you can write 18 to be 2 into 3 square, and you can write it as 1 cube this, 1 to the power 12 this. So it will not have unique representation, unique prime factorization if you treat 1 as a prime number. 1 is not considered as a prime number. Okay, this is why we don't consider 1 as a prime number. Okay, so this proof is also existence proof, existential proof. Okay, it means how to find these primes, that is not discussed. That is, there is no algorithm to find the factorization, unique factorization. Okay, actually, given a very large integer, getting this factorization is very difficult problem, a very hard problem, and many crypto systems are designed based on that fact, that you will not be able to factor that number very easily. Okay, we don't have any efficient efficient means polynomial in the size of your a input a, that you can factor it, you can get this factorization. No polynomial time algorithm to factor a composite number. So existence proof. So there exists a positive. There exists this factorization and another uniqueness proof. If you given this ordering of prime numbers, then this is unique. Positive integers. So using well ordering principle, you can. I have used well ordering principle. This can be proved using induction also. You can just go through the proof. I will not discuss this. You just go through the proof. Alternative proof is using induction also. There is this proof can be done in several ways. Using induction, we also can prove this using strong induction. Anyway, I will skip this part. Okay. Now Euclid's theorem, there exist infinitely many primes. We have infinite supply of prime numbers. Okay, so one proof is given. There are several ways this theorem can be proved. You go through this. Okay, I will not discuss this. Using Euclid's lemma, you can prove this. Another. Okay, so this one I want to. So some problem, how to solve some problems using prime number theorem. Already I have mentioned what is the prime number theorem. Prime number theorem says that if you have an integer x, and then pi x denote the number of primes less or equal to x. And that number pi x is almost equal to limit of pi x divided by x by ln x. Limit of pi x divided by x by ln x is almost is equal to 1. That means suppose this is your x, pi x can be approximated by x divided by ln x. So the theorem was pi x divided by x by ln x, that limit as x tends to infinity is 1. Okay, so pi x can be approximated by x divided by ln x. it can be greater than this, it can be less than this also. Okay, so this theorem was stated in earlier classes. So using this prime number theorem, how to estimate the number of 50-digit prime numbers? To estimate the number of 50-digit prime numbers. So how many 50-digit prime numbers are there? Okay, so how many 50-digit numbers are there? All the 50-digit numbers are in between 10 to the power 50 and 10 to the power 49. Okay, so 10 to the power 50, 10 to the power 50 essentially means this is 51-digit number, and 10 to the power 49 is 50 digits. So 10 to the power 49 to 10 to the power 50. Within this range you get all the 50-digit numbers. So all the three-digit number. So 10 to the power 4, between 10 to the power 4 and between 10 to the power 4 and 10 to the power 3. So for all the 3-digit numbers you get between 10 to the power 4 to 10 to the power 3. 1000 to 100. It begins from 100 essentially. Okay, so same way, 50-digit numbers, they lie between 10 to the power 50 and 10 to the power 49. So how many prime numbers are there? 50-digit prime numbers are there. So up to 10 to the power 50, how many numbers? How many prime numbers? Pi 10 to the power 50. And up to 10 to the power 49, how many prime numbers? Pi 10 to the power 49. So how many primes are there, which are 50-digit numbers? These are pi 10 to the power 50 minus pi 10 to the power 49. And you can approximate it as this. 10 to the power 50 by ln 10 to the power 50 minus 10 to the power 49 by ln 10 to the power 49. So approximately this value. Okay. So I have another problem also. Suppose we select a 50-digit odd integer. Randomly you select 50-digit odd integer. What is the probability that it is a prime number? Okay, so when we discuss RSA or many other crypto systems, we have to choose a prime number, a very large, say 1024 bit prime number. So we will select some number, odd number, and what will be the probability that it is prime? Okay? So you can estimate this probability using the prime number theorem. Okay, so 50-digit odd integer, if you choose 50-digit odd integers, so how many 50-digit odd integers there? 50-digit integers are 10 to the power 50 minus 10 to the power 40. These many 50-digit integers. 50-digit odd integers means this divided by 2. Even integers we are discarding. So this is the total number of 50-digit odd integers. Possible odd integers 10 to the power 50 minus 10 to the power 40 divided by 2. And between means how many 50-digit prime numbers are there? Already we have calculated. So this is the favorable number and this is your total number of odd integers, 50-digit odd integer. This is the 50-digit prime numbers. So this is 1 by 64. Okay, so if you pick a 50-digit odd integer, then the probability that this number 50-digit odd integer is essentially a prime integer, the probability is 1 by 64. Okay, so chances of selecting a prime 50-digit prime is 1 by 64. So I'm giving you 2 exercises. You do this using the prime number theorem. Estimate the number of 300-bit prime numbers. Or randomly, suppose we were to randomly select a 300-bit odd integer. Estimate the probability that we select a prime. number. Okay, so in factorization based crypto systems, we generally choose means for RSA we will see we choose 1024-bit prime number. So how to choose that? If you choose, what is the probability that it will be prime number, and how to be ensured that it is prime number? So how to check the primality of an integer? So those things we will learn. We will learn.